of this, right?
Okay.
So what I'm going to do is I'm just going to not substitute, but it's called induction, to where I think that this is correct. I can't disprove it, so I'm going to use induction and basically substitute it for what we have over there in blue, okay? So does everybody see that what I have boxed in blue, those are identical to one another by mathematical induction, okay? So I can write this as 3k, k plus 1 divided by 2. Okay, that's what all of this stuff is, okay? It's not substitution, okay? There's a difference in math between substitution and induction. Induction means that we don't know for sure that it's true, we assume that it's true, okay? So does that make sense, guys? Substitution we know is true, okay? But unfortunately with induction, in other words, this inductive hypothesis, we think it's true. We have no reason to think anything to the contrary, okay? I'm going to write this next. I'm just going to have 3k plus 1. Okay? So this guy just comes down here, or girl, I don't want to be gender biased. Okay. So guys, if I wanted to justify that step, I would either say induction. Okay? Actually, I would say induction. And then the other step that we have over there, that's just a basic computation, the k plus 1 plus 1. Okay. So this is the process for the induction so far. Okay, I don't think I've lost anybody with this. Every time, whenever you guys do an induction problem, you're going to substitute this, even though it's not substitution. You think of it like substitution. And you're going to substitute the right-hand side back in for this potentially very lengthy number of terms. All right. Now, we're still not done, but at least we have a punching chance to get done with this because the rest of it's algebra. I need to make the left-hand side look like the right-hand side of this. Okay? Does anybody think they might know a way to start?
Bring it the right side to the left and make it equal to 0?
Well, no, we don't want to set it equal to 0. Let's just work on one side, just like a trigonometric proof.
Okay.
Maybe we want to hold one side constant.
Multiply both sides by 2?
That's one way to do it, or we can just get a common denominator for the right and the left-hand side and then try to merge it together. Either way you want to do it, okay? Technically, in a mathematical proof, you want to hold one side constant and then operate on the other side, okay? Just like, and I don't know like how many of you guys remember doing the identities in trig, but when you prove an identity, you should hold one side constant and not mess with the other side. So I'm going to do it the classical way. If you guys multiply by 2, that's fine with me, okay? So let's do this. Let's get an LCD of 2. So, the first term stays 3k, k plus 1 over 2. What about that second term? Instead of 3 quantity k plus 1, what's that going to become, guys? 6 quantity k plus 1, right? Basically, if you give it a denominator of 2, you multiply the numerator by 2, right? So this is going to become 6 quantity k plus 1 divided by 2. And then we can go ahead and say that that's going to be equal to whatever we had on the right side to start with. Okay. So does that hurt anybody's feelings, or is that okay so far? Okay. So let's make this into one mega fraction now. I mean, that's the whole purpose of getting a common denominator. Okay. In fact, if you guys wanted to skip right from the inductive step to this next step that we have, you certainly can. Okay. So just by addition. By the way, we're 2 steps away from getting done this problem, okay? So by addition, this is going to become 3k, k plus 1, plus 6 quantity k plus 1, divided by 2, and that's going to be equal to the right-hand side. Okay, so let me get out of your guys' way. I'm going to make up a little bit more room for myself. Like I said, 2 more steps, algebraically, maybe even 1. Okay. So, we still want to make this left-hand side look like the right-hand side. And there's 2 ways that we could potentially do that. Okay? Does anybody think they might have an idea of what to operate on the left-hand side? And there's, like I said, there's 2 ways to do it. I'm going to try to show you guys an efficient way, but I bet you guys know a couple ways to do it. So, what's one thing you guys might do? Go ahead, Paul.
Can you factor out 3?
We could not only factor out a 3, but what else, guys?
K.
3 quantity k plus 1. Very nice, gentlemen. Okay? Guys, is it obvious to everybody that 3 and 6 share a factor of 3? is it obvious to everybody that k plus 1 and k plus 1 share a factor of k plus 1, right? So we can factor that out as a GCF. What's another way that you guys might be able to do that?
You can multiply it out.
Foil it out and then do like the factorization that way, okay? I don't care which way you guys do it, but I think I like John and Paul's way of doing it a little bit better, to where you look for a common factor and pull it out. It'll save you guys 2 or 3 steps, okay? And we want to be efficient, okay? That's just a nice word for lazy, okay? So, if I were to factor out the greatest common factor of 3 quantity k plus 1, guys, if you factor out 3 k plus 1 from this first term, guys, what are we left with in the first term?
K plus
Just
2.
k, right? So I'm just going to be left with a k. If I was to factor out 3k plus 1 from the second term, what are we left with there, guys?
2.
2. Okay? If you don't trust me, just go ahead and FOIL it back out. Okay? And then on the right-hand side, we're looking for 3k plus 1, k plus 2 divided by 2. All right. So guys, it's a little bit simple, okay? But you're going to look for sometimes binomial factors. You're going to look for like GCFs a lot of times when you have these fraction sort of problems. Okay? Is everyone okay with the factoring here, guys? Okay. If you can't see the factorization, make sure you see me after class so I can help you see that a little better. Or maybe what Mr. Weber was saying is just FOIL it out and brute force it from there. Okay. You might be able to do your trinomials better than your standard GCFs. Okay. Guys, we've shown it to be true, right? Isn't this sort of like division into cases? We had a basis step and then we have an inductive step. We've proven them both. Okay, so, therefore, by the basis and inductive steps, the formula is true. You don't have to write this down, I'm just writing something that... So, maybe something like this. What was it? You guys remember seeing like a geometric series, right? And for those of you guys that are suffering through Calc 2, and it has a form, right? It's all, what is it, 1 over, A over 1 minus R, right? You can prove the sum of a geometric series true by using mathematical induction, okay? Now the problem is because it's infinite, it's difficult to do, okay? But you guys could be able to prove that, okay? So for those of you guys that are suffering through any Calc 2 stuff, eventually you'll see your series, and that might be helpful for you. But anyway, I just wanted to tell you guys in real life that this does have applications. It's not just something that math people come up with to torture you guys, okay? All right. What's that? Well, Calc 2 was developed to torture everybody. Yeah, sorry about that. Okay. Questions I can answer, guys. Okay. Now, obviously, we need to see more of these, okay? So, by the way, on a scale of 1 to 10, this guy was about a 2. I never give anything a 1 from induction because, well, it's just all different. All right, so let's beat up another problem, okay? So, this time, I'm asking you guys to prove that the sum of the first n perfect squares is equal to this mess right here, okay? Maybe some of you guys in Calc 1, how many of you guys did like the Riemann sums in Calc 1 where you had to like do you actually had to find the forms of the rectangles and try to add them up that way? You might have used this formula at some point to write it, okay? We're actually going to prove that formula, okay? I kind of cheat my Calc 1 class out of doing that because it's just kind of unnecessary. Regardless, okay. So here's our proof. We need a basis step. Okay. Let's just use n equals 3, just because. And then from now on, we'll just go ahead and use the first element in the domain from now on, or after this case, okay? So our lowest element in the domain could be 1. Let's just do 1, 2, and 3. So let's let n equal 3. This means that 1 square plus 2 square plus 3 square should be equal to 3, 3 plus 1, 2 times 3 plus 1, all divided by 6. Well, let's hope that's true.
How do you decide what n equals?
That's a good question, okay? John, I can make n equal anything I want as long as it's a number in the domain, okay? I could have used 1 if I wanted
As
to.
long as n is greater or equal to 1.
Correct, sir, okay? I'm only using 2 and 3 initially just to show you guys how to get these to work. After that, we'll just use 1 from now on, okay? But I just wanted to make sure, like, if for some reason another one of your teachers says, use something other than the most simplistic case, then we've done that. Okay, does that answer your question, sir?
Yeah.
Okay, good. All right, if we compute this out, and of course it's addition, so you might not want to trust me. 1 plus 4 is 5, 5 plus 9 is 14. On the right-hand side, 3 times 4 is going to be 12. 12 times 7 is going to be 84. 84, 6 is 14, I believe. And so I can verify. Oh, it should be multiplication. I should be okay with that. Adam, is that good?
Yeah.
Okay, thank you, sir. And guys, last time I checked, 14 does equal 14. Okay, so right there, guys, that's easy to do. We can all do that no matter who we are in this class. I know you guys can. All right. Step 2 is the inductive step. We have to assume that this holds true for all n equals k. Okay, so step 2, and again, for the first couple times, I'm just going to put this in brackets. This is the inductive hypothesis. We assume, it looks like the result holds for small values of n. Okay, so we're going to say the result holds for small values of n. In other words, we can't find a counterexample, okay? Not that we tried very hard, okay, but we could if we really wanted to try hard, but we would assume that it works if we find something small and it works, okay? Now we assume the result holds true for all n equals k. Okay, so let's go over here, we'll erase some board. So let's assume the result holds true for all n equals k where k is an integer. Okay. Thus, the sum of the first kth perfect squares, so 1 square plus 2 square plus 3 square plus da 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 plus k square now is going to be equal to k, k plus 1, 2k plus 1, quantity, quantity, divided by 6. Okay. Now, that's an assumption. Okay? We don't know that for sure, but we can't find a counterexample. Okay? So, let me give you guys a minute, copy that all down. Okay, so everybody's good with the preliminary stuff. No questions about basis, no questions about inductive stuff. Okay, now comes the fun part. And when I say fun, I mean, this is the part you want to pull your hair out of. We have to show it true for n equals k plus 1. Okay, so this is where we make our money with our algebra. Okay, so 3, we want to prove for n equals k plus 1. Let's let n equal k plus 1 by substitution. Let's go ahead and make sure we can write this. Okay, so by substitution, does anybody think they might know? Well, I'm going to write out what we initially had, so let me do that. So we have 1 square plus 2 square plus 3 square plus da 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 plus n square is equal to n plus 1, 2n plus 1 over 6. Okay, that's just the original that we were given. Does anybody think they might know what's going to look, or what it's going to look like after we perform the substitution where n is equal to k plus 1? Mr. Hart, go ahead, sir.
N plus 1 square plus n plus 2 square, right, on the left-hand side?
Well, Say it one more time for the entire thing.
Okay, on the left-hand side,
Okay,
it will become like 1 square plus 2
Uh-huh.
square
yes, sir.
plus 3 square
Yes, sir.
plus da 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 n plus 1 square.
Not quite, you're really close, okay? Somebody help him out, you're really, really
Plus n
close.
squared, or plus k squared,
Uh-huh.
Oh, k square, yeah.
plus quantity k plus one
Nice.
squared.
That's the only thing I was missing, that K square.
Close.
Okay, very nice job, Mr. Weber, okay? Guys, does everybody see how they did that with that, okay? All they did was they just went up to K, so they just basically plugged in K for N, and then they just added on one more term, the K plus 1 term, okay? The right-hand side, don't we just go ahead and substitute K plus 1 in wherever we see an N? Now be careful, okay? I'm gonna write this up incorrectly, and then somebody yell at me as to why I write this up incorrectly, please. So K plus 1 quantity, K plus 1 quantity, 2K plus 1 quantity, divided by 6. Okay, so let me let you guys copy it down, and then I'll let somebody yell at me. But what did I do incorrectly there, unfortunately?
It's the parentheses around K plus 1.
Yeah. Guys, and a lot of students unfortunately do this. Right here, when you have 2 times n, and they substitute k plus 1, please, please, please don't forget that it's the quantity of k plus 1, okay? And then unfortunately what will happen if you forget to do that, your proof's not going to look right, or it's not going to go right, and then you're going to get really upset because you went through the whole problem, all right, and you'll start cursing my name even more than you already do, okay? I don't need that. My soon-to-be ex-wife is already cursing my name and taking my money anyway, okay? Oh, it's okay, don't worry, she's rich. Questions I can answer, guys. Everyone's good with being able to substitute up to the k plus 1. Everyone's okay being able to substitute k plus 1 on the right side. Okay? So after this, most students do really well if they get this far. All right. On the right-hand side, can't we just simplify the numerator a little bit? We're not going to FOIL anything out. We're just going to write it as k plus 1, k plus 2, 2k plus 3 over 6. So let's go ahead.